Start பண்ணலாமே. Start பண்ணலாம் சார்.
Okay, madam.
Good evening to all. I welcome esteemed guest of honor, respected principal, dear professors, organizing secretaries, and my dear participants. I extend my warm welcome to all of you present here for 2 days online workshop organized by the PG Department of Chemistry, VSS Government Arts College, Pulankurichi, Tamilnadu. I want to thank our respected principal, Dr. P. Muthuswamy, for giving us skillful encouragement as well as the complete creative freedom. I welcome you, sir. I welcome our today's person, Dr. N. Vasimalai, Professor of B.S. Abdul Rahman Institute of Science and Technology. I welcome Professor Govind Raj, Associate Professor of our college, to deliver the vote of thanks. I welcome you, sir. I welcome the programming secretaries, support us in many ways, not only helping with the ideas and giving us the necessary moral support, betterment of my work. There will be a question and answer session at 7:30 p.m. where the participant can ask questions and can engage in conversation with our speaker. You can also post your queries in chat box. Participants are requested to keep your video on mode and audio in off mode. Once again, I welcome you all. I hope that you get to enjoy the day with all of us. Next, the session over to our principal. I welcome our principal to deliver the presidential address. I welcome you, sir.
அனைவருக்கும் இனிய மாலை வணக்கம். VSS Government Arts College, Pulankurichi Chemistry Department சார்பாக இன்றும் நாளையும் நடக்க இருக்கின்ற இந்த 2 நாள் ஒர்க் ஷாப் ஏற்பாடு செய்து நடத்தி கொண்டிருக்கின்ற கெமிஸ்ட்ரி டிபார்ட்மெண்ட் ஹெச்ஓடி மதிப்புக்குரிய ரமாதேவி அவர்களே, இந்த 2 நாள் ஒர்க் ஷாப்பில் கருத்துரை வழங்க இருக்கின்ற டாக்டர் வசிமலை அவர்களே, இந்த 2 நாள் ஒர்க் ஷாப்பிலே கலந்து கொண்டு பயன்பெற இருக்கின்ற ஆய்வாளர்களே, மாணவர்களே, பேராசிரியர்களே, அனைவருக்கும் என் இனிய மாலை வணக்கம். பூலாங்குறிச்சி VSS கவர்மெண்ட் ஆர்ட்ஸ் காலேஜ் சார்பாக இன்றும் நாளையும் நடத்திருக்கின்ற இந்த பயிலரங்கிலே கலந்து கொள்ள இருக்கிற அனைவரையும் கல்லூரி முதல்வர் சார்பாக வாழ்த்தி வரவேற்கிறேன். இந்த நிகழ்ச்சியை பயனுள்ள வகையிலே நீங்கள் எல்லாம் பயன்படுத்திக் கொள்ள வேண்டும் என்று அன்போடு கேட்டுக்கொள்கிறேன். நல்லதொரு கருத்துரை வழங்க இருக்கின்ற டாக்டர் வசிமலை அவர்களை கல்லூரி சார்பாக வாழ்த்து மகிழ்கிறேன். எங்களுடைய கெமிஸ்ட்ரி டிபார்ட்மெண்ட் ஹெச்ஓடி ரமாதேவி அவர்களுக்கும் அந்த துறையை சார்ந்த பேராசிரியர்களுக்கும் என்னுடைய வாழ்த்துக்களை தெரிவித்துக் கொள்கிறேன். இறுதியிலே நன்றியுரை வழங்க இருக்கின்ற பேராசிரியர் கோவிந்தராஜ் அவர்களுக்கு என்னுடைய நன்றியை தெரிவித்துக் கொள்கிறேன். நல்லதொரு தலைப்பிலே இன்றும் நாளையும் இந்த பயிலரங்கு நடைபெறுகிறது. இதை கலந்து கொள்ளுகிறவர்கள் நல்ல முறையிலே பயன்படுத்திக் கொள்ள வேண்டும் என்று அன்போடு கேட்டுக்கொள்கிறேன். நல்ல நிகழ்ச்சிகளை காண்பதும் கேட்பதும் இன்றைக்கு அரிதாக இருக்கிறது. இந்த ஒரு நல்ல வாய்ப்பை நம்முடைய கல்லூரி ஏற்பாடு செய்து தந்திருக்கிறது. இந்த நல்ல வாய்ப்பை நீங்கள் எல்லோரும் பயனுள்ள வகையிலே பயன்படுத்திக் கொள்ள வேண்டும் என்று அன்போடு கேட்டுக்கொண்டு அனைவரையும் மீண்டும் ஒரு முறை வாழ்த்தி விடைபெறுகிறேன். நன்றி, வணக்கம்.
Asimali sir, you can start.
Okay, madam, can you hear me? Anybody at me? Can you hear me?
Yes, sir.
Hello.
I hear you, sir.
My voice is audible?
Yes, sir.
Yes, audible, sir.
அனைவருக்கும் இனிய வணக்கம். நமது முதல்வர்
Sir, one second.
Yes,
sir.
madam. Yes, madam.
I will continue, sir.
Yes, please. Yes, please.
So it is my honor and pleasure to welcome our resource person, Dr. N. Vasimalai, to deliver his speech on fluorescence spectroscopy and current research in fluorescent nanomaterials. Few words about our speaker. Dr. N. Vasimalai is now working as assistant professor at Department of Chemistry, B.S. Abdur Rahman Crescent Institute of Science and Technology, Chennai. He has completed his UG and PG degrees in chemistry at Vivekananda College, Madurai, and received Best Student Award for both degrees during his period. Then he completed his MPhil and PhD degrees at Gandhigram Rural University, Dindigul. After the completion of PhD degree, he worked as postdoctoral fellow at the National Ching Kang University, Taiwan. Then he received globally renowned fellowship of Marie Curie Fellowship in Europe and worked at the International Library Nanotechnology Laboratory, Portugal from 2015 to 2018. He has published more than 30 research articles in the high impact factor of 98.2 and height index is 11, the international journals and 4 book chapters. One of his articles has been highlighted in Nature India. Now he is guiding for 4 PhD students and completed 4 major projects. Moreover, he has an immense skill in analysis and instrumentation. He is also a PhD co-supervisor of Malaysian student in University of Mara, Malaysia. He is an editor of May Web Journal of Chemistry, Canada. He is also a member of ACS and reviewer of ACS, RSC, Elsevier, Springer, Wiley, Oxford journals. He has delivered several talks in national and international institutions. Currently, he is running some projects, including one from Tamilnadu State Council for Science and Technology. His field of specialization has been focused on the synthesis and characterization of fluorescent metal and metal oxide nanoparticles and their biosensor and biomedical applications. So it's my pleasure and honor to welcome our research person to deliver his speech. I welcome you, sir. The session over to resource person.
Thank you, madam. Thanks for your
you,
nice introduction. So, as our principal start with Tamil, I am also want to start with Tamil. என்னை தரணிக்கு அறிமுகம் செய்த என் தாய்க்கும் இத்தரணியை எனக்கு அறிமுகம் செய்த என் தாய் தமிழுக்கும் முதல் வணக்கம். அனைவருக்கும் இனிய மாலை வணக்கம். Good afternoon to all, because many people are seeing by YouTube from foreign also. So therefore, I'm not able to continue in Tamil, so I have to tune to English. So first of all, it's my pleasure to thank VSS Government Arts College, their management team, especially the principal sir. He has given very nice introduction, principal address, as well as his fullest support to conduct not only this program. Madam said that Madam has conducted several programs with his fullest support. Thank you, sir. And the convener, Mrs. B. Ramadevi, my special thanks to Mrs. P. Ramadevi, because Madam has conducted me several times, including this morning and 1 hour before. I know the well, the conduction of program, it is not an easy job. So we have to take care of all the things. Many problem will come, including internet, including electricity, as well as some personal issue. Many things can come. But the speaker, the arrangements, as well as other things, the convener has to take care of it. But Madam done very well, as well as Madam has given very nice introduction about me. Thanks a lot, Madam. And Madam find me through one professor from Sahir Hussain College. So he's my friend only. So Jayamurugan sir. So in this session, I would like to thank Jayamurugan sir also and all the faculty members for their fullest support. And one more thing, I want to convey my gratitude to the VSS Government Arts and Science Arts College, because many people are there from IIT, IISc, big professors are there, but they are giving me a chance to deliver a talk as like a young professor like me. So this is a great opportunity for me. And also they found the potential persons. They have conducted several programs. So this program is a 2 days workshop program. Very nice title, and it is recent days it is a leading one. The title is Fluorescent Spectroscopy and Current Research in Fluorescent Nanomaterials. And tomorrow also I'm going to give. So I have divided into two sections. During my talk, I can tell what are the things I'm going to do now, and tomorrow what are the things I'm going to teach you. So it is a kind of workshop. So regular webinars means it's just like a lecture, but this workshop we have to learn something. If it's a regular workshop, then I can bring you into the laboratory, or I can bring some chemicals and I can show you how to synthesis. But it is online webinar, so I thought that to convert this one for the learning of data interpretations, as well as the calculation of quantum yield and other things. So these things, it's very important for the fluorescence field. So I will teach that things one by one. Meanwhile, I can go with the fundamentals as well as the recent advances and what we done our laboratory, and what about our impact factor of our published journals. These things we are going to discuss by today. So as Madam during his her introduction, she said I'm from BS Abdur Rahman Christian Institute of Science and Technology. This is my email ID and phone number. For any clarification or future collaboration, you feel free to contact me. And also you can contact through our program organizer Ramadevi Madam also. And this is my background. So all the things Madam already said. And so the reason I'm not having the very good background, like my father is a big officer, my mother is a big officer. It is not, because I'm from small agriculture family. Well, in the 2004 in my village, myself only is a first graduate. So just imagine in that village, so the level still we have only minibus facility, don't have other facilities. So that much remote village. But now I reached this good position and I got globally renowned Marie Curie fellowships and many things. There is some hard work. So if you are keep on do the hard work, if you are not getting the benefit today, one day you can get it. Many young researchers are here, and many people are having little problem to get the job. So what I want to convey to them, so do your hard work. Don't expect the benefits. So one day you can get that gaining. So don't expect today. Your duty to do the hard work. And also proper planning is very important. If you don't have a proper planning, there is not good things. If you are doing PhD or some other things, you have to keep a very good contact with some relevant professor. If you are working with fluorescent spectroscopy or fluorescent nanoparticle, you must have a collaboration with other faculties. If they are IIT or other big institute, then it's hard to find and hard to get the collaboration with them. But you can go with the your level, like deemed university or state university, other things. But all are very interested to collaborate with many people. It's based on our approach only. If you are approaching, even you can get it from IASC also. So it is easy. So this is the very very good message I want to convey through my talk. And this is the International Iberian Nanotechnology Laboratory. I was there in Portugal for 3 years. This is a small country, Portugal. Two side it's covered by the uh, two side covered by the Spain and two side Atlantic Sea. See here, the capital city is here. Look my cursor, and the place of this International Iberian Nanotechnology located in the Braga North, Portugal. Very nice place. And this is only one nanotechnology international research laboratory is there in the European Union. They have several department. They have all the facility. If you are looking this view from the sky, it's look like a 10 power minus 9. So you know, well, 10 power minus 9 is a nanometer scale. So look, this one is the head of the 9, and this tail is the 9 tail. So you can see this one, very nice place. And I was there with environmental monitoring groups. You see inside circle, it's me. I was there among 10 ladies, and this is my boss Begonia Espina, and all are my friends. And still we have a very good communication. We have a research collaboration also. So everything is possible when you do the hard work. That day I did not get the gaining, but after I reached the Marie Curie fellowship, then I enjoyed the European Union life. So sophisticated life, and weekend 2 days holidays, very good salary, and up and down flight fare it is free, and allowance also given for my wife and my child, even they are in a home. So many things you can get it. So one day you can enjoy all the things if you are doing hard work today. Okay, we can go with our title. 2 days online workshop on fluorescent spectroscopy and current research in fluorescent nanomaterial. You know very well about the fluorescence and other things, but the basic fundamentals, if you are very familiar, guys, just think this one is a small revisions. Otherwise, if you are want to learn something, then I can discuss that things. The first one, electromagnetic spectrum. See here, electron and magnetic force, this is called electromagnetics. So electromagnetic spectrum, if you are looking here, so distribution of the continuum of all radiant energy can be plotted either a function's wavelength or frequency. In short, that is the electromagnetic wavelength. Many people have seen one end this upper helix and another one is the lower helix, go like this. So then if you go inside, the X-rays, it's a shorter wavelength, and microwave radio waves is the longer wavelength. I can give one example. See here, this one is. So X-ray and gamma rays, so these are all, these two, it's the shorter wavelength. See here, the bottom shorter wavelength. When you are going visible, especially ultraviolet, visible, and infrared, microwave, and radio waves, their wavelength is the this is a shorter, and this one is the longer one. So you can see here this one longer waves. So that's why the radio waves people are easily they can hear the radio from sky or from long distance. They can able to hear it because it is the longer frequency. So electromagnetic spectrum is the range of all possible frequency of electromagnetic radiations. EMR, electromagnetic radiations, extends over a wide range energy and wavelength frequency. See here, it is wide range energy. I can give the scale, which is scale gamma rays, and which scale is the the radio waves. In nanometer or micrometer scale, I can give here. See here, this is the scale. From here, gamma rays is the shorter wavelength 0.01 nanometer. So 0.01 nanometer is nothing but 10 picometer. So 10 picometer, 10 power minus 12 meter, that level. It is a very smaller waves. So it's a very shorter wavelength, picometer size wavelength. When you are going X-rays, it is 1 nanometer only. Then ultraviolet, it is increasing 100 nanometer. Then visible light, it is a millimeter size. Okay, then if you go with infrared, 1 millimeter, microwaves 10 centimeter, then radio waves 10-meter distance you can get it. And booster other things, if you are giving in the telecast sections, then you can able to hear these radio waves, or you can able to receive these radio waves with a long distance. This is the scale. Okay, based on the scale, people are applying for several applications. We can go one by one. So radio waves, where we are using, it is well known that radio waves, they are emitted from the radio stations, and you can tune your favorite tunes. Then radio waves are also emitted the stars and gases in the space. That is secondary case. But this one we can easily receive from the long distance. And microwave, whichever we are cooking at our home using the microwave oven, that is called microwave radiation. You can cook popcorn or anything, coffee, many things. So it's based on the microwave. It is another one longer wavelength. The very longer one, radio. The next secondary one, it is the microwave. Then infrared waves. So infrared waves we can divide into three categories. One is the we can divide into two categories. One is the near infrared and far infrared. Then near infrared, again it is two categories. Near infrared is called as a NIR infrared, near infrared, NIR rays. So that rays you can divide into two categories. One for the first window, and the another one is the second window. The first window scale, if you go back, see here, this is the infrared. This is a millimeter scale. So this millimeter scale, if you check with the zero point 0.1 millimeter is equal to 100 nanometer. Okay, zero point 0.1 millimeter is equal to 100 nanometer. I guess you are agree with me. Then 1 millimeter is equal to 1000 nanometers. So 1000 nanometer is that. Okay, I can come to the points. So in this 1000 nanometer, from you start here, it is from okay, 100 to 1000 nanometer. Okay, infrared. In that case, if you go inside near infrared rays, you can find the nanometer from 700 to 950 nanometer. 700 to 950 nanometer is the first biological window. 950 to 1300, it can go be higher than 1000. So 1300 nanometer, it is called as the secondary biological window. So it is hard to prepare the nanoparticles having the absorption at infrared range. I mean 700, 600, 800 or 1000 something. If you are getting the particles higher than 1000 nanometers, you have a lot of biological properties. You can apply for the lot of biological properties. For example, drug delivery, cancer therapy, other things. Why this one is that much novel, sir? We can go one by one. So this ultraviolet and visible light, somewhat it is the toxic. But when you are go with the infrared rays, it is not a toxic. And microwave somewhat okay, because people are using to cook the microwave. So therefore, the infrared rays people are using for the cancer therapy. The reason, even if you are going, I can show this one. The infrared rays, night visions, Google's pick up the infrared light and emit the skin. Then infrared lights helps to make the uh, if you are going for hospital for back pain, the doctor they can advise you to take a massage. You don't need to go for Kerala to take oil massage. That massage is different. That massage is called as a light massage. How they are using, you know, well, the lamp will be there. In that lamp is infrared lamp. Then outside 3 4 classes will be there, the strong class, the thick class. Then if you have to switch it on, and the heat can be generated through the infrared rays, then you wherever you are getting the pain, that part you have to put, and 1 minute, 2 minutes, or 1 second, 2 seconds, and you can move to the other part, and you have to repeat it for 5 times, 6 times. This is called infrared radiation massage. It is the clinically it is approved one. The reason this infrared can easily penetrate into our cells. Then when it is penetrate inside of our cells, it will not be harmful to the cells. But in case one ultraviolet rays, if it is pass inside of our skin, then that skin can die. Otherwise, we can get the cancer. That is also a problem. That's why the foreign ladies are applying the sunscreen in their face, because when they are going for sun bath in a beach, so a lot of UV radiations will come. So in their body, they are applying this sunscreen. Inside of the sunscreen, if you look, then titanium dioxide will be there. That titanium dioxide and carbon nanomaterials will be there. So if these materials will not allow the UV radiations inside, then it will be reflected. Because of that purpose only, the sunscreen people are using. Okay, come to the infrared rays. it is not a harmful to the body. Then second one, it will be easily and deeply penetrate into the cells. It's not like other rays, it's deeply penetrate into the cells. These things it is needed for biomedical applications. I'm very sorry, my camera is little poor, so you don't need to look my face and you just look my slide. uh, you have to take this type of nanoparticles for biomedical applications, cancer therapy, bioimaging, other things. If you do the bioimaging in the visible region, somewhat okay. But if you are doing that with red regions, it is very good applications you can apply, because you can keep on irradiate infrared, even though your cancer cells will not die. The same one, if you are keep on irradiate UV light, maximum cancer cells can die. Then it is hard to apply in our body or mice body. So infrared rays, it is very, very important for biomedical applications. Then some examples, you see gamma rays. Okay, this one is the X-rays. These people are using for medical applications or radiative materials. And X-rays, you know well, the bone fracture, or we can apply for even teeth and many things, take X-rays. And another one is the UV lights. UV lights, it's interrelated with our fluorescence. In other slide, we can study that UV. So UV light is important. Then visible light with GR, it is there. Then infrared rays. These are all the infrared rays, remote control and other thing. Medical applications also there. Then microwave rays, your mobile phone, other things, microwave, and then radio waves. These things, radio waves. So these are the direct applications people are using based on the frequency. If the frequency is higher, then we can apply. So 1 millimeter size infrared people are using for biomedical application. Visible light, UV lights also, it is important for the fluorescence spectroscopy. We can go one by one. So electromagnetic rays in the range from 0.4 micrometer to 0.7 micrometer is known visible regions. I'm going to talk only with visible regions. So these visible regions, starting point from here to here, 0.4 micrometer and 0.7 micrometer. 0.4 micrometer is nothing but 400 nanometer. 0.7 micrometer, 700 nanometer. We can say 400 nanometer to 700 nanometers, the known visible regions. Okay, so below than 400 is the ultraviolet regions, UV region. So we have to consider above 400, and after 700, I told you after 750 or 700, it will come up for the in a NAR regions. So this is the infrared rays, 750 something. Then 400 to this one, the 7 colors you can find it. WIB-GR, you can get it. Violet, blue, indigo, green, yellow, orange, red. That is, you know very well. And less than 700 is the ultraviolet regions. Visible region somewhat okay, it is not that much harmful, but ultraviolet region, it is harmful. You know well, if you go back with our the environmental studies, you know the stratosphere, troposphere, and many layers are there, ozone layers. So these layers can protect the radiations of the ultraviolet rays. That's why we are safe. So this is the important things. If it is not protect, then directly the exposure of ultraviolet will be there to our body, then other live beings, then it will be toxic to the all the live beings. So UV ultraviolet rays somewhat toxic, but visible region it's okay. Then if you are going very particular about that area, so the more in depth, this one I told you 400 to 700 visible regions. And what is the region for violet? What is the region for blue? What is the region for green? That things I given very clear one. So visible regions, it's a 400 nanometer to 446. I mean 0.4 micrometer is nothing but 400 nanometer. That's why I told you. So this violet region is 400 to 446 nanometer. Visible 446 to 500. Small changes only. 500 to 578 nanometer is the green regions. Since 578 to 592 is the yellow regions. Then 592 to 620 it is the orange region. and 622.7 nanometer is the red regions. So if you are getting the peak and absorption spectrum around 400 to something 500, it is the blue color. So the original color blue. Then if you are getting this region, it is the original color green, and this region it is the yellow. So we can easily conclude it if you know these values. So among these, blue, green, and red are the primary colors. This one, blue, green, and red. Okay, and you know, well, in traffic signal, people are keeping the green and red, then yellow. The red is the longer wavelength, so people, if they are coming with long distance, they can able to see that light. That's why they given. If they are giving violet, then when they are close to the traffic signal, that time only they can able to look that light. These are all the purpose the people are using these red lights for the uh, stop signal. It is not only India, it is a global, the global network. So where whichever country you go, the red signal is for the stop and green signal is for the start, and yellow slow. So this is the common for all the countries. The reason is the red color is the long wavelength. Okay, come to the basic for the fluorescence. These things we studied, previous things we studied about the colors and absorption and other things. Now we can go for the fluorescence. So first one, who has invented or who found this word and who has given this word of fluorescence? The term fluorescence comes from the mineral fluorescer. Fluorescer means calcium fluoride. Calcium fluoride is the name is called fluorescer. Then the scientist Sir George G. Stokes, he observed in the 1852. So this one is called fluorescer. That's why he has given the fluorescence. Fluorescence, the meaning is the off visible light. When the fluorescer, the meaning is calcium chloride. Then when the half visible light, when the exposure to the electromagnetic radiation, the ultraviolet, then it is become a fluorescence. So the fluorescence, if you want to find whether your compound is fluorescent or not, naked eye view not able to find it. You have to go with the ultraviolet rays. People are using, the organic people are using this UV chamber, ultraviolet chamber, to monitor the DLC, the reaction, how much it's went and how much unreacted materials there, the spot they can check. So for that purpose, the UV chamber they used. Another one chamber, iodine chamber, so that is different. So the same UV chamber you can use for your material testing. So you have to take it in a glass, and that glass should not have the any fluorescent property. And the lid, many lids, I have observed the many lids, they have a fluorescence property. You have to remove the lid and put inside, and before you put, you have to check your glass alone whether it is fluorescent or not. If the glass alone, if it is fluorescent, don't use that glass, because inside if you are giving water or something, then whichever color is there in the glass, then it will be transfer inside and it look like a your material is a fluorescent, but it is not correct one. So the background you have to know. So what about the only glass? If the glass doesn't have any fluorescence property, then you can add your nanomaterial inside. Then don't use lid. Even if you are using the lid, you have to check the lid itself, it is fluorescent, because they are adding lot of things inside, then it is fluorescent. Then the color, if you are observed green or yellow or something, then you can preliminary confirm your particles having fluorescence property. Then if you go inside of UV chamber, two lamps are there, three lamps, you know, well, one daylight, another short UV, and another one long UV. 250 it's a short UV, and long UV 360 or 320 will be there. So you have to check it in both. Sometimes majority of the cases short UV will show some color, but when you go for long UV, it will not show the color. So if you are observed that contrast color or something, you have to go for the fluorescence spectroscopy, and you have to excited some excitation wavelength. If you are getting the peak, then it is 100% confirmed your compound it is fluorescent. The meantime, you have to know about your solvent fluorescence. For examples, if you are using DMF, dimethyl formamide, many reports are there. DMF itself, it is a fluorescent. Then if your compound inside of DMF can show the color, but you would think that it is a fluorescence color of my compound. So whenever you go inside, you have to check the blank. What about even if you are using water? It is not needed to check, but when you PhD students, when they go for Viva, some people, if they ask, if you have data, then no need to worry about anybody. So yes, we checked with solvent water doesn't have any fluorescence. So therefore we have confirmed my particles only having the fluorescence property. And second one, when you go inside of fluorescence, there are two categories. One is called dye molecules. So dye molecules, isobond molecules, rhodamine B, iuramine, and methyl orange. These are all the dye molecules. These dye molecules also having the fluorescence property. That is different case. But nanomaterials, if you go nanomaterials like cadmium sulfide, carbon quantum dots, gold nanoclusters, cadmium telluride, zinc oxide, zinc sulfide, many things. If you go that directions, then you have to know what is the difference between these two and the two. We can come for the organic dyes molecules. Organic, majority of the organic dye molecules only soluble in organic solvent. DMF, DMSO, or other acetonitrile you have to take. This solvent itself, it is the fluorescence. So you can apply for other applications only, but you cannot able to apply for biomedical applications as well as biosensor applications because it is toxic to the live cells. You have to find that way. But when you go for the nanoparticles, you don't need to worry. Wide range of applications you can use. Biomedical application, biosensor application, light emitting diode applications, solar cell applications, many things you can use. So these are the major difference. And one more important things, the dye molecules, majority of the dye molecules, if you check the cytotoxicity. Cytotoxicity means cell toxicity. If you are adding 1 grams of your compound, how much cells died in that particular area, we can count it. Typically, three replicate time we have to take. That is called cytotoxicity. Majority of the report, we found that these organic molecules, it's toxic to the live cells, but nanoparticles not that much toxic. So this case also we have to keep in your mind. Okay. Then the fluorescence, it is the three types. We can say one is called fluorescence, another one is phosphorescence, the next one is the chemiluminescence. So three types are there. And one more is that bioluminescence. Bioluminescence is naturally occurring, if some insects, if you find nighttime, it is lighting. So that type of things is called bioluminescence. We don't go with that level, but chemistry level, fluorescence, phosphorescence, and chemiluminescence. So luminescence is the emission of light by the substance. It may be solid or liquid. This substance may be solid or liquid. So the emitting property, if your compound or materials having, that is called fluorescence. It may be solid or liquid. It occurs when electrons return from the excited state to ground state. That time it loses their energy by the way of collision or to the surrounding. Surrounding means mediums. That is called fluorescence. These details we can study in the Jablonski diagram. The fundamental one of fluorescence, it's the Jablonski diagram. So this is the basic principles of Jablonski diagram. You are very familiar with the Jablonski diagram, so I don't want to go very in depth. But few things I want to confirm. The one is the singlet ground state. Singlet ground states means the spin is the opposite spin. You can find it. Singlet ground state. Then singlet excited state, opposite spin, you can find it. Then triplet state, unpaired electron in the same spin, you can find it. These three things, it's very important. Singlet ground state, opposite spin, and the singlet excited state, unpaired. This is the pair, and this is unpaired, opposite spin. And triplet excited state, unpaired, but same spin, you can find it. This is the basic principle, how it is returning. See here, this one, singlet. So this singlet 1, singlet 2, singlet 3, something there. And it's a triplet, triplet 1, triplet 2 is there. So these molecules, if it is getting energy, then it will go up singlet state or triplet state. Then inter system crossing will be there. Then final product, this one is the fluorescence. These molecules is the fluorescence. But intercrossing, this one inter system crossing, if it is happen, then it will come for the triplet state. Then again, it is called as a phosphorescence. Okay, these things you already studied, so I don't need to explain much more. But this one is the fundamental singlet ground state paired, but the spin is the opposite spin. This one singlet excited state, so opposite spin but unpaired. Triplet state unpaired, same spin. Okay, the principles of fluorescence. The principles of fluorescence already discussed. When it is going the excited state, if it is happening the inter crossing, that time it has to lose their energy to the by the collision of two molecules or to the uh, environmental. I mean the medium. Then it loses their energy. Then because of that energy, it has to come down. And if it is the singlet 0 to S2 and S0 to S1 and S1 to S0, triplet to S0. So if this is happening from the triplet to S0, S0 is the ground state. So triplet state to ground state, it is the phosphorescence, this case, from triplet to S0. In case S1, singlet 1, 2, ground state, it is the fluorescence. But absorption, this one absorption from S0 to S2 or S0 to S1. This is the absorption. But fluorescence means it started from S1 to S0. Phosphorescence should come from the D1 to S0. This is the basic fundamental. Then vibrational T activation takes place through the intermolecular collision at the time scale of 10 to 12 seconds. So faster than phosphorescence. Sorry, faster than fluorescence. Then internal conversions. The internal conversions already I discussed the electron transfer from the singlet 1 to then triplet state. This is the intercrossing. This intercrossing, it's commonly internal conversion. So internal conversion commonly happens when the energy is loses. Then Stokes shift. This is very important one. So if you are having one compound, even dye or even nanoparticles, first one we have to take a UV visible spectrum or absorption spectrum. Both are same. Then you have to take the emission spectrum. For UV visible spectrum, hope you have much experience. You have to fix first blank solvent. If you are using water as a blank, you have to put inside. Then you have to remove second time. Then you have to add. You have to keep only your sample. This is the common one. But when you go for the fluorescence, the cuvette is different. Hope you have seen the UV visible cuvette is two times two side is the transparent and the other side is a little rough surface. But fluorescence cuvette, its four side is the smooth area. It is a little expensive than or more expensive than UV visible cuvette. And also this absorption cuvette, you can touch in the the rough surface. You can hold in the rough surface. But this emission cuvette, it's four side transparent. If you hold in the two side and whichever they are in your finger and fingerprint, that part also sometimes can. So what we have to do, you have to hold in the corners, any two corners, opposite corner, you have to hold and put inside. So these things, these much minute things also you have to keep in your mind. So absorption, if it is coming 300, the emission, if it is coming 600, the difference between the absorption and the emission, that is called Stokes shift. For example, this one is for the 600 and this one is the 300. 300 nanometers difference is that this is called Stokes shift or excitation emission difference. You can find it. Generally, people what they commonly written, if their absorption one area and the emission maximum is coming with 50 nanometer difference, and another one is coming with the 200 nanometer difference or 300 nanometer difference. Which one is the hood fluorescence, and what way we can distinguish these two? If it is near to 50 or something, this absorption effect also will come in the emission. overlay will come. That is tomorrow we can study. That is called fluorescence resonance energy transfer. Three kind of mechanism is there. If your molecules obey that three kind of things, then you can say this is due to the fluorescence resonance energy transfer. But the distance, if it is 100 nanometer or higher than 100 nanometer, then your molecules is having the very good fluorescence nature. Also you can say it's less photo bleaching, other things. The Stokes shift is very important. Majority of tie molecules will not have more than 100 nanometer difference. These absorptions also will reflect in the emissions peak. So the mirror image, see here, this is the absorption spectrum and this is the emission spectrum. The overlay is here. This type of overlays commonly happen for fluorescence resonance energy transfer. And not only this overlay, three rules we have to, this system has to follow. Tomorrow we can study that things. And this is the absorption. So absorption is coming 1, 2, 3, 4. Now we have a doubt which one we have to take as a excitation wavelength. For examples, when you go and take a emission spectrum you don't need to keep a blank. Directly you can take, the system can nullify the blank. In that case, what you need to do, you have to give the excitation wavelength. It will ask excitation wavelength and slit width. Okay, so here take example, this one absorption, and this one absorption, this one absorption, this one absorption. Four absorption is there. Which one is the correct one to give us a emission maximum? So the people, if they are giving this one, the first least one, sometimes they can get the very good emission. Then emission intensity, y-axis intensity will be higher. Okay, sir, this one is lower and this one is lower and this one is the lower. So can I take this one is the excitation wavelength? Yes, you can take. But if you are going for a high impact factor general, what they are asking, what way you can tell this, for example, this area, uh, 300 nanometers. So exactly 300 nanometers, how you find this one is the correct excitation wavelength? Why don't you keep 305 nanometer as a excitation wavelength? Or why don't you go for 290 nanometer as a excitation wavelength? Then what we need to do, from here 200 and this is ended at 600, just imagine. Okay, so in excitation, if you are going fluorescence spectroscopy, then you can go with the different excitation spectrum. That one option is there. For example, in a Fluoramax or in Jasco, then Shimachu, these instruments having that facilities, you can give the 10 nanometer reference. It will ask from which nanometer to which nanometer you have to take a emission spectrum with this much interval excitation. Then you have to give from 200 to 600 nanometer. Then each difference of excitation wavelength of 5 nanometer. Then it will give. Then you just plot in the three-dimensional view whichever excitation or which excitation giving the maximum emission intensity. You have to choose that excitation wavelength as a excitation wavelength. This is the correct way to find the excitation wavelength for your emission spectrum. But many people are simply taking the hump to obtain here, this hump obtain here. Many reports say that this one only given. That is not correct one. This case is commonly happen for these materials, cadmium sulfide, cadmium selenide, semiconductor materials, carbon materials, something. But the exact reasons you have to give the wide range emissions, then it will come. So when you are exciting with the different wavelength, but the emission maximum obtained in only one place only. The same peak will come for the all excitation wavelength, whichever you find here. But only difference emission maximum, this x-axis only, this y-axis only will be varied. For example, if you are giving this one, the small peak obtained here. This one little higher intensity. This one maximum. So therefore, this one obtained maximum emission intensity. Therefore, I have chosen this one is the correct excitation wavelength. That way only you have to give the excitation wavelength. But some people are taking based on the hump also. My question, if exactly 320, do you have any data for 330 or 325 or 315? then we have to do this one. If the people are asking, this is very simple. It will take just a half an hour or 40 minutes time. This facility is available, whichever the instrument I mentioned, you can go inside. Otherwise you have to do by manual. You don't need to remove the sample every time. Only you have to change the excitation wavelength. This data, if you have it, it's a very good answer to choose the excitation wavelength. The excitation wavelength, if you are not choosing properly, then the entire system, sometimes the quantum yield calculations and other things will be a problematic. So therefore excitation wavelength selection, it is very very important for emission spectrum. Then second one, you have to merge it together. This is the absorption spectrum and this is the emission spectrum. If you are finding the overlap here, then it may be the fluorescence resonance energy transfer. Also, you have to look the Stokes shift from which excitation you have given and which excitation, which emission maximum obtained. For example, here I given 350 and here I obtain 700. The difference is 350. It's a very good system. If they both are maximum 50 sinking, that case you can expect some photo bleaching properties will be there. This type of things you can find it in the dye. So if you are taking the dye, then photo bleaching it's there. Okay. Then type of fluorescence: Stokes fluorescence, anti-Stokes fluorescence, and resonance fluorescence. The Stokes fluorescence, as I mentioned here, the ground state and excited state, it started one point and ended the same point. This is called the Stokes fluorescence. And anti-Stokes means it loses some energy, but it is not come for the S0, but it is there in the S1 or S01 or something. That is called anti-stoking. And resonance structure is, if we are getting little higher energy, that one is the resonance fluorescence. Because of the resonance structure, you can get it. Then molecules. So after seeing the molecule, you can have some idea whether this molecule is fluorescent or not. What ways are, if you are finding azo bond inside, then majority of the cases it will be there. And catechol and benzene structure or some anthracene structure, majority of the cases you can find it. But anyway, whatever it may be, you just dissolve with particular appropriate solvent and go for the UV lamp. You just switch on and you have to irradiate short wavelength, check the color, and long wavelength, check the color. If you are getting the very good fluorescence, then second time you just check with only solvent. If you are getting very good fluorescence, then it is not due to your compound. Solvent itself having the fluorescence. If you are not getting any fluorescence there, it's very good. Also, you have to cross check with your glass vial also. Sometimes we have observed some plastic vials, F&F tube or something itself, it has some fluorescence, blue fluorescence. If you put something inside itself, it will show the flow fluorescence. So we will get a confusion. That case, we have to check one by one, one by one, one by one. Then finally you can find it. The same one, if you go for a solid state application, you just make it a solid. That solid substance you put in the glass plate and put inside. Again, glass plate itself, you have to check whether it is fluorescent or not. If that compound is having the fluorescence property, definitely your compound having the fluorescence. Then you have to go for the fluorescence spectroscopy to check it. These are the some fluorescence compound. See here this quinolic structure and the catechol structure. If you getting the majority of cases, this one is there. But our study is only related with fluorescent nanoparticles. Okay, sir. Fluorescent nanoparticles. Whether we can combine with some enzyme? Yes, you can. Whether we can combine with DNA? Yes, you can. So it will mix with the anything. It is called a darket. Darket means, if you go a little in depth with biochemistry, whichever the virus, whichever the bacteria, or whichever the cancer cells it is there, and you can see inside the receptor, antibody, antigens, and many things there. You have to modify accordingly. That is called a target. The folate is there. Folate is the receptor of cancer cells. But if you are making your nanoparticles the outside folic acid, then it have the interaction with the folate receptor. automatically it will go and bind with that folic acid. Then you can find the cancer cells. That is called targeting. You are able to find the target, the cancer cells. So this is very important. Why, sir? So once it is reached inside, once it is reached inside, then the normal cells, well, it's not a fluorescence, but dyed cells, it is a fluorescence. Some fluorescence can come, but this one is the red fluorescent, your compound. Then even though dyed cell is somewhat green fluorescent, this one red fluorescent. So then you can find where your nanoparticles present, whether it is lungs, whether it is kidney, whether it is brain, or it's a tail of mice. That things you can find. Then how much inside is that, that much in-depth studies we can go. This kind of field is called bioimaging. So bioimaging, if you having the red fluorescent compound, it's a very good one. We can keep on irradiate for long time, even though the normal cells and cancer cells will not die with this infrared radiation, because it can go easily penetration only with your materials. So materials effect you can find it, that much application. So combined with the recognition of the targeting and the tune of their antibody, antigen, something. Even we can some reports available. The people are using islands. Well, the people, they don't want to use the glass on their eyes, so they just use islands inside. But that is other way, when they are cleaning or when they are touching the eyes by their finger, sometimes they can get a bacteria affection. So that type of bacteria the people already reported. uh, that type of bacteria things, if you are modifying with this nanoparticles or something, then it is little toxic to that bacteria, then it can kill. The same times your eyes can protect from the bacteria affection. Some reports are there. It's a lengthy study, the medical university people, they have published. Then detections, biomolecule detections, as well as other toxic chemicals detections. Many things you can do, even explosive detections, dinitropylamine or picric acid, that things, many things we can do. Then analytes, already I told you the bioimaging, mitochondria imaging, cell imaging, and other things. This is called some kind of a bacterial virus, is something you can do. Then fluorescence related terminology. What are the things we have to keep in our mind when you are expert or when you are started to do the fluorescence? One is called excitation. So initial one, I have synthesized one nanoparticles. Okay. I have to check that particles whether fluorescent or not by UV chamber. Yes, it is fluorescent. It is a red fluorescence. Okay. Then you have to go for the emission spectrum. In that emission spectrum, we have to confirm whether it is emittive or not. Again, the problem is which excitation wavelength we have to give. So first, before we go for the emission spectrum, you have to take UV visible spectrum. In that UV visible spectrum, you have to find wherever you find the peaks and which range. It is started from 200 and ended in which range. Then you have to note it down. Whichever the peak you obtain, directly you give that peak's wavelength as a excitation wavelength. Check the fluorescence spectrum. This fluorescence spectrum, already I told you, emission maximum point will not be changed. Only the intensity can increase or decrease based on the excitation wavelength. It is only one case for the metal, inorganic nanoparticles, but carbon quantum dots is a different case. When you are changing the excitation peak, the peak position can change. That is the different case. But all other fluorescent nanoparticles, including dye, the peak positions will not be changed. Only the emission intensity, y-axis intensity, can be varied when you are tuning the excitation wavelength. So that time, even though if you want to confirm very clear, whatever I said in my previous slide, 5 nanometer reference, you have to keep it. Then finally, you can get the maximum value of time. That is the important one. Then excitation coefficient, that is important. Efficiency of absorbing optical energy. This value is wavelength dependent. So it is just like a theoretical calculation. So excitation coefficient, energy efficiency of absorbing optical energy, is value of wavelength. excitation wavelength dependent, whichever I discuss here, the same one. Then emission, process of releasing optical energy. Once it go for the excitation and excited state, then it has to come for ground state. When it is coming the ground state, if it is go through the IC, that is called fluorescence. ISC, that is called phosphorescence. Then quantum yield, this is very important. So today I'm going to teach you, sorry, explain you how to calculate the quantum yield. This is very, very important. The reason, the people, if you are saying fluorescent particles, at least you have to report quantum yield or um, lifetime. So lifetime only some places are there. For example, Ultra First Center in Chennai, Taramani campus, the previous director Ramamurthy sir, uh, there you can get it, but the getting slot sometimes is difficult. But the quantum yield you can use, you can calculate through your you have to do one experiment, and you can do it with your fluorescence and absorption spectroscopy. That is enough. If you are reporting that one, even people are not asking for the fluorescence lifetime. In our paper, one paper we have published the impact factor 9, so there we are not reported the quantum yield. All of my, sorry, we are not report the lifetime. All of my papers, we did not report the lifetime. Only we have reported the quantum yield. uh, the reason, this one is easy, we can prepare, and we can do by ourselves by theoretical calculations and the experimental values. Then Stokes difference in energy between the excitation and the emission wavelength. Already I told you. The excitation and emission wavelength difference. This is the Stokes. The key to contrast the generation. Then spectrum, whether it is the broad spectrum or it's a sharp spectrum, through that way also we can distinguish the fluorescence properties and other things. Okay. Then next slide. So see here, this is the excitation wavelength. See here, this one is the around 590. Then emission wavelength it's obtained here, so 540. The Stokes is this one 40, and this one is the 1050 only. These are di molecules, rhodamine B molecules. The Stokes is the 50 nanometers. So the so energy radiations, excitation, and the emissions you can use this way. And you can couple these two datas in one data using origin software. It is very easy. Then scale, you have to keep it same scale, and this intensity maybe up and down, it is not a problem, but the maximum, this is important. When you are taking excitation spectrum only you can able to take it by your fluorescence spectroscopy only. We don't have a separate instrument to take a excitation and the emission, two different modes. You can find it in the fluorescence spectroscopy. But absorption, you have to go for UV visible or absorption spectroscopy. That is different. So therefore, even though if you don't have a UV visible, you can use this excitation spectrum. This is also same, but the peak position, I mean the peak shapes, it is different. It's different from UV visible. Then excitation spectrum and Jablonski diagrams we already studied, and this the luminescence and the fluorescence and the phosphorescence. We have to know little more about this one. There are three main forms of luminescence: one fluorescence, phosphorescence, and chemiluminescence. The fluorescence and phosphorescence are two forms of photoluminescence. We discuss clear. One it is coming with the IC, then another one is ISC. This is a fluorescence. You know well, the lowest excitation state S1 to S0. Then the 10 power minus 9 to 10 power minus 6 seconds only it will be happen. But phosphorescence, it is the long one, so it can go higher than minus 6. It's a different one. Chemiluminescence, when you are mixing two chemicals, that time if you are observing some fluorescence property, that kind of things is called chemical luminescence. If one chemical A alone no fluorescence and B alone no fluorescence, when you are mixing or when you are giving heat or when you are changing some reactions condition, if you are getting some fluorescence that is called chemiluminescence, chemical luminescence. It may be oxidations or reductions or fluorescence, resonance, energy transfer or charge transfer. Anything can happen, and you can use catalyst also. Some people are using catalyst enzyme to produce this chemiluminescence also. Experimental part and calculations of quantum yield. It is very, very important. This is a workshop, so therefore I can explain well clear manner how to calculate the quantum yield. Before I go for the quantum yield, maybe I can share this. Uh, okay. Are you able to see my screen? I'm in Google. Ramadevi, madam. Anybody, any participants, please answer me. Are you able to see my screen? Quantum yield.
Yes, sir. Yes, sir.
Okay, madam. Thank
Yeah.
you. So this quantum yield, there are two types quantum yield calculations. One is called relative quantum yield, and the another one is the absolute quantum yields. So one you can do by instrument. The Fluoromax instruments, they have an accessory. You don't need to do any theoretical calculations. How you are taking your sample. So similar way you have to insert inside. Then separate tube will be there, that is for fluorescence quantum yield accessory. If you want to buy that one, you have to pay a little extra money. Then that instrument will ask you which solvent you have taken, which temperature you kept, and the refractive index of the sample, that things it will ask. You have to fill all the things, excitation, emission range you have to give, and starting to end how much you taken, that details you have to give. Then finally you can get your quantum yield. So if you are having the Fluoromax, I don't know about other Jasco and other things. They are also saying that they have Jasco. I use a lot when I do my PhD. That time I use Jasco. Also I use Fluoromax when I was in abroad. Also abroad, Fluoromax. Many people are using in many countries. That is a very good one, Fluoromax. Um, for other instruments, sometimes you can get some big noises, but Fluoromax, I haven't seen that type of things. If your compound is fluorescence, if you want to confirm fluorescence, the Fluoromax is better, but they expensive, very expensive instrument. Other instruments, you just having a confusion means you just cross check with the UV chamber. If you are getting UV chamber, for example, already we discussed, if it is green color, then it should come around 500 nanometer emission something. If it is blue color, then less than 400 nanometer it will come. So that's why I given in my initial slide this range and this range. So according to that way, you can conclude, okay, we observed red color of emission in UV chamber. So it should come around 700 or higher than 700, around 650 to 700 or something. Then if you are keeping that idea, then if you are peak in the same range, then you don't need to worry. So it is theoretically matched, and also the experimentally that is red, and this one also red range. So that way you can calculate this fluorescence quantum yield. Uh, Two ways. One is that way. Then if you don't have that option, then what you need to do, you have to download this one, this paper. It is in Google only. It is free one. The Fluoromax company only, they have this one. Just a second, I am opening. Otherwise, I can go. Quantum yield calculation. Just type as quantum yield calculation. Then come down. This one. A guide to recording fluorescence quantum yield. This paper. Okay. look here, www.chem something. I can, if possible, I can put it in the chatting box, this link. I can go with the chatting box. Okay, you can get it in the chatting box, this link. So this is the data. So guide, this one from Hariba Fluoromax only. Fluoromax, the name, but it is a Hariba company. It's from UK. So they have given very good these things. After I cross check with abroad faculties as well as Indian IIT faculties and many faculties, this one only they are referred. So it is not my own recommendations. So many people are using this one. So you don't need to worry. And we have published many paper using this site only. So we have given this website link as a reference. So you don't need to worry. It is already followed by several people. Big site is. So this one guide, just to have a look introduction and other things, I can go inside what we have to do. So this is the simple procedure. So what we need to do. It is there in my slide also. Maybe I can go inside. After that, I can come back with this one also. Okay. So experimental and other things. So procedure, what you need to do. So you have to take a solution. For example, so I am using silver nanocluster and I want to calculate the silver nanocluster fluorescence. You don't need to measure correct volume. So randomly you just take 1 ml and 1 ml water you just take it. You know well the UV cuvette it is 3 ml volume. So 2 ml you have it. Take UV visible. But that UV visible absorption should come less than 0.5. See here, absorption should come less than 0.5. Until it's come, you have to dilute it, dilute it, dilute it, dilute it. But the same times you have to maintain the 2 ml as a volume. Hope you understand. For example, first 1 ml silver nanocluster, 1 ml water I added, but my absorption is the 2. Then what I have to do, 1.5 ml I have to take from that cuvette and I have to discard it. The same 1.5 ml water I have to add inside because I need a 0.5. So then randomly I calculated is 3 times extra. Then I just check it. It is not exactly to maintain 0.5. 0.6 it's okay, 0.4 it's okay. Therefore it's randomly you have to do. Okay, sir. In that conditions, I observed the peak, I mean the intensity absorption. It is around 0.4. Very good. So you have to keep that one as a first one. So it should be a 0.1. Simple one. You have to take a absorption with 0.5. One concentration you have taken. You know well, first initially you have taken 1 ml, then diluted to 1.5 ml. I removed and diluted. So you got 1 peak. The same solution you have to take the fluorescence with already you fixed the excitation wavelength. Before you fix the excitation wavelength, don't go for the fluorescence quantum yield. First you have to fix the excitation wavelength, whichever I said with the different excitation wavelength. Then you have to fix it. The same excitation wavelength you have to use here. It is for your compound. Then you got some peaks. You don't need to worry about this intensity because the fixation of absorption it is very important. If corresponding the absorption if you getting this one. And one important case if you are using Simachu, Jasco, this absorption will not go more than 1,000 only the maximum intensity of fluorescence. That case what I got to do, sir, do one thing. First fix the fluorescence, dilute, but kept that total volume is 2 ml. Then it will decrease only because it's a dilution process. Next addition decrease, next one, next. So keep at around 900 or 800. Then the same solution you come for the absorption. Even if it is 0.15, don't worry, you keep that one also. For this Jasco or Shimachi case, But fluoromax, it will go with 4,000, 40,000 something. So that case, you don't need to worry. So if it is going good, then go this direction. If it is higher than 1,000, it will be saturated. That case, you dilute first and fix the fluorescent. The same solution come again here. Okay, sir, that is the solution one. Go back. Record the UV visible absorption spectrum with the solvent background and chosen sample, and it should come with the less than 0.5 concentration. I mean absorption. Okay. Then again, the same solution, you have to record the fluorescence spectrum. Then you have to record that fluorescence spectrum. This is a second case. So one experiment, one solution. Okay. Then you have to take another one solution. The previously we have taken 1 ml, then 1 ml water. Again, you just go that calculation, 1 ml and 1 ml water. From there, you have to take 0.5 ml. Now you just take 0.4 ml because it's decreasing order. So 0.5 you kept and 1.5 you order. Now you just keep 0.4 and 1.6 now you add. Slowly it will be decreased. Okay, the same one you have to take here, the fluorescence also will be decreased. Now you have to take, say, third one. This time 0.3 you have to take, or 0.35 you can take. Then remaining, the remaining up to 2 ml, you have to calculate it. And here also, this one is the, again 0.25 something. And this one is the, it is your wish. It is not mandatory to keep exactly this one 3.5 and this one 3, this one 2.5, this it's not needed, but slowly decreases, it is needed. The same one, you same solution, don't discard it, and don't waste even 1 drops of solution. You just go. What we used to do, two instruments, it's there at our laboratory. We switch on the two instruments, and then if I use this one, immediately the same solution I can go back with this one. Anyway, you have to transfer into the keyword, the different keyword. But while you transfer, use pipette. So totally you will get the 6 readings, or it is better or advisable to take a 10 reading. So slow decrease. Maybe this one is the large decrease. You can take 2 readings from here. Slow decrease by the dilutions. If this is okay, then you go for fluorescence. That one should be the below than saturated level, 1,000 for Jasco or Shimachu. If it is coming less one, then it is fine. So 10 readings you have. Then what you need to do? Step 1, step 2, repeat for several times, at least 5 times they ask. Step 1, this one, the first one. Step 2, this one. They have to ask us to repeat it. We got it. Okay, fine. Okay, this is finished for your sample. Now you have to take for the blank. So how we have to take a blank? So blank, it is important. See, this is in that paper, you can see the background. I can show you that paper also. It is there in our website. So this is that reference paper. Go down. The last page, this paper is there. A table of standard materials and their literature quantum yield values. So this company, they have given these values. Okay, sir. I can have it in my slide. Here, see the wavelength range. So my emission 600 to 650 in this range is there, sir. Emission maximum. Okay, sir. Sir, mine it is 400 to 600, 600 to 400. First, you have to choose the compound, standard compound according to your emission wavelength, and also availability of chemicals. For example, my range, I got the peak around 550. Okay, even if you have the compound 400, 450, 500, 550 up to 600, you can choose the quinine sulfate. So my compound 550, what are the things it is possible to take it? These two it is not possible, and this one it is possible. Fluorescence somewhat okay. Then this one is possible, Narhammer, and this one Harman, and many things are there. But I have to check what are the chemicals available in my lab. and cost in case if you want to buy. We don't have a stock for these things. Only we have fluorescence and quinine sulfate and rhodamine B. So this one it is matching. So then it is cheap cost. I can buy the quinine sulfate. This way you have to choose the reference. The availability of chemical or cost of the chemical, and it is based on your emission range. You have to choose the standard. Majority of the cases we choose the quinine sulfate, but it's higher than 400 or higher than 600 means we have to go with other zinc phthalocyanine also sometimes we have taken. The another slide, you just go here. Here see zinc phthalocyanine, it is 750, 600, 750. This one it is available. So we have taken for red fluorescence these three. So according to your things you can take. Even benzene, see here up to 300 only. How they have fixed it is already reported by some papers. Journal of Physical Chemistry 1983 they have reported, they have quoted this one. So they are not take by themselves, it is already reported one. They chosen this one and they found this much concentration and this much quantum yield they found. Okay. So now I have taken quinine sulfate as a solvent blank because it is obtained at 550. Okay. Then you have to dissolve with this solvent only. It is reported one. You have to follow this solvent. 0.1 molar sulfuric acid you have to take it. If you are taking your quantum yield value, these persons in this paper they have reported 0.54 quantum yield. So 0.54 means 54 percentage of quantum yield they have obtained, and rhodamine B is 100 percentage, and this one is the Norharm 58 percentage. This one is the 45 percentage. So this is the idea. But if you are reporting, sometimes the problem can come when you do the calculation. So 3 times, 4 times you got to repeat it and check with the reported one. For example, if I am reporting gold nanocluster 100 times or 100 percentage fluorescence, nobody can believe, because the dice molecules only still now reported 100 percentage. We must have the literature survey idea also. In case if you go with the literature survey, how much is the silver nanocluster they have reported? 10 percentage, 20 percentage only, sometimes 30 percentage. So our range should be in that range. If somewhat extraordinary case 40 percentage, 80 percentage, you have to repeat it 1 or 2 times and check again, check again. If you are reporting somewhat novel data, if range it is the same one, don't need to worry. So whichever it's you observed, but you have to repeat and check reproducibility. If it is obtained, then you can go, because it is a theoretical one, experimental as well as theoretical. Okay sir, I got it. Then again you have to go UV visible for that solvent, I mean the quinine sulfate inside a 0.5 molar of sulfuric acid as a solvent, then emissions this way. So you got 6 readings or 10 readings for your nanocluster, you got 10 readings for your blank, and here also you got 10 readings, and here also you got the blank. Okay, now you can go for the calculations. The calculations, this one is the calculations. So the gradient, this is the quantum yield of your sample, quantum yield of standard. Now you got the quantum yield of standard is the 0.54 according to this literature report. So you got to fill it. And gradient X and gradient standard. What is mean by gradient and this one? It's a surface coverage is the gradient. Surface coverage, how to calculate, sir? See here the absorption. X-axis is absorption. Y-axis is the fluorescence intensity or integrated fluorescence intensity, nothing but surface coverage. Come back. So here you given the excitation wavelength 560 something. Which excitation wavelength you have given? The same place you have to check it. Don't need to worry about even this place. Sir, my excitation wavelength 650. So you just see the corresponding absorption is 1.14. So this one only reverse, and another one and another 1.5 or something. So this absorption only you have to take it, whichever you given as a excitation wavelength. That range only you have to take. Don't take other peaks, only excitation peak. So that one we have given in the x-axis absorption. Okay, fine. Then fluorescence, take this graph, only one graph. Go by origins. In the integrated area, you can find the area of these peaks. That is called integrated area. So area, if you find it, this first peak, the area this much, and this peak area this much, this peak area this much. So finally, you can get it this straight line. In that straight line, the slope value you have to take as a gradient of sample, gradient of standard, because you've done both. Then refractive index of sulfuric acid, you have to go by internet and you can check it. Refractive index water, water is our sample, so you can take it. So if you simplify this equation, then you can get the quantum yield. How much percentage it will be? Some 0 point digits. So that is the quantum yield. This type of quantum yield is called as a relative quantum yield. This type of quantum yield is called a relative quantum yield. Then another one, if you are doing by the instrument, that is called the standard quantum yield something. So in that case, you have to mention whether you calculate by this one or that one. You just refer our paper also. In a slide, I can show that one. This is a simple way to calculate the quantum yield. If you are reporting this calculate, majority of the cases they are not asking the lifetime. Even though if they are asking, you can able to answer it. We don't have a facility, we have given quantum yield, and many reports are available with the quantum yield. So we got high quantum yield, so therefore our materials quantum yield. All of our papers we are not reporting the fluorescence lifetime. Unfortunately, we did not get the opportunity to take that one, but we tried with many places. This quantum field it is okay, and already I given the examples. We went up to the 9 impact factor with this data only. Okay, then research output from my labs. So this is our Journal of Hazardous Materials. Recently we have published, and my students Marudh Pandi, he has published. Impact factor is 9. So after you see this paper, we don't have any special data, but the designing of work is very important. So you know well the nanoparticle synthesis hearts. Look the word for our title, 1 minute synthesis of nanocluster. So this is our task. Within a minutes we have prepared nanocluster. Then why it not go for the impact factor 9? Definitely it can go. Based on my knowledge, only one report or two reports available with 1 minute synthesis. But we synthesize by simple sonication. Even we are not sitting. Simple sonications we have prepared. That technology we have developed. This is one great novelty. Then second one, we have prepared the on-site monitoring using smartphone aided paper-based kit. This is the important one. Smartphone aided paper-based kit. You know well these days people are going everywhere along with uh, mobile phone. Don't mistake me to say excluding toilet. So smartphone always the people are keeping in their hand. So why don't we use that technology using smartphone? It's like a pH paper. Then it's called on-site monitoring. If you want to measure the some toxic level, sulfide or mercury level in water, we had to bring the sample and give to the laboratory, and we had to check it. But if you are having the mobile phone and this small paper, you can test it in the spot. That is called on-site monitoring. That technology also we have developed. So these are the two major advantages or novelties of our paper. It went high impact factor, and inside I can show wherever we tune our work and what way we are differ from others. So this is a simple synthesis protocol. So what we taken copper nitrate and ascorbic acid we have taken. So Marudupandi also from Vivekananda College, Solavandan. And so after he joined, that time only he learned nanotechnology. I used to take several classes for him, and he's also done hard work. And this work entirely decided by him after he discussed with me, and I given some ideas. Then he tried several times. Finally, he achieved this one. Then this is the Ligon TG. This is the dio-BT glucose. This the sodium is the counter ion, but after it's went out and it's be S minus. This one it's bind on the surface. Then sodium hydroxide we have taken, and copper nanocluster is produced. Okay, without using ascorbic acid, yes, we done, but nanoparticles only produce. Without using sodium hydroxide, yes, we done, but nanoparticles only produce. Without using TC, yes, we done, nanoparticles not produce. Without using copper nitrate, yes, we done, but nanoparticles not produce. So what we used to do systematical study. This one it's the A, B, C, D. So what we studied, what's the effect A alone, B alone, C alone, and D alone. Thereafter A plus B and A plus C and A plus D. Then ABC and PC, PCD. That way we done. Then finally nobody can ask any questions. So ask the question as a reviewer. If this paper come for me, what are the question it is possible to ask? That question ask my student, and I force him to do it. Then automatically it will go. So this type of, if you are doing research, this type of things you have to think by yourself. You consider as a reviewer, and you have to ask. Then you can easily avoid the unnecessary questions. Okay, then simple sonic acid, 10 second and 20 second and 25 seconds, within 1 minute you can get it in your hand, nanoparticles. It is a fluorescent particles. See here it is in the daylight. The photographs already discussed copper nitrate A, B, C, D and A plus B, and that way we have taken. It's a B, C, D, something we have taken. So nothing happened with that one. The final one, it is the nano cluster, it is the green one. See, it's in the UV light. It's a UV chamber only. We don't have any special instrument to take these photographs. We just use our smartphone only. Okay. Then these are the corresponding photographs, and the last one is the nano cluster. See here, hump only it is obtained 1, 2, and again we have confusion which hump we have to take as a excitation. In that case, what I said, from it is from 300 and it is entered almost 600. So start from 300 to 600 with the 10 nanometers, 5 nanometers, different excitation interval. Finally, where you obtain the emission maximum, that way you can take it. This is the absorption. See here, this is the emission. See here, the emission, as I discussed earlier, it comes under around 450. So the 450, it is the visible regions only. It is green color. So whichever I observed in the green color, the same data I obtained for the emission. So therefore, it is correlated. So you don't need to worry about further data. It's formed. That things we can do it. It's daylight and UV light. And after binding thioglucose, we check their frequencies. See here, SH it is binded, and this one after nanoparticles produce, the same one it is there, but intensity is decreased. It means that after several was it's went out, and it is the only TC. So this one will have strong band, and the other bands are there. It is for the thioglucose. And XRD patterns for cluster, it's obtained. It is reported already. It's matched with the reported one. It's crystal structure we obtain. And see our particles. If you are saying cluster, particle size should be less than 3 nanometers. So small particles you obtain here. And this is the particle size histogram. It's not comes in the fluorescence spectroscopy. If it is there, then next day I can discuss. So if some possibilities there, in my another talk I can teach you how to do this particle size histogram. You cannot calculate by your own. Some software is there. I will teach you in case if someone invite me. This group, please touch with admin. Then through the admin, Ramadevi madam, I can post you. So here we obtained this particle size is 2.5 nanometer. So therefore it is fluorescent. It is a nano cluster. Okay, crystal lattice we obtained. This is the lattice. It's like a fingerprint. 0.21 nanometer is the exclusive property for the copper. Copper crystals can come 0.21. That's why we got the crystal and amorphous structure. It's a broad band we obtained. So here see all are not crystal. This area only it is crystal, and other area somewhat amorphous. So both are structure is there. And this one selected area electron diffraction pattern is not a complete crystal because the plane not good, somewhat amorphous also we obtain. Then we check with the time after 10 minutes, 20 minutes. It's the time effect, the fluorescence time effect. Whether if you are keep on irradiate the UV light, sometimes fluorescence property can be quenched.
So it is the photo quenching. So in that case, we have to check it 1 hour. It is enough. We checked with the several times, and these particles, it's after 10 minutes. This is the time effect. We kept with the different time. We checked, and it is the stable for many 6 minutes. Uh, no. This one is for the preparation of nanoparticles. It's the mercury. See here, copper nanocluster in the presence of mercury. So we checked the interaction with the mercury, how long it will take. 1 minute, it's highly interact, 2 minutes interact, and 3 minutes, it's completely quenched. Thereafter, there is no quenching. So 3 minutes interaction is enough for the mercury interaction. And this is the sulfide interaction, because we optimize mercury and sulfide. It is the interaction. One is on fluorescence, one is off fluorescence. So that's why this case is 5 minutes needed. It's based on the compound concentration and the analyte concentration. See here the mercury. After addition mercury, the fluorescence was quenched. It's completely quenched. Okay. So this is the mercury deduction based on the fluorescence quenching. We got the clear systematic quenching according to the correlation coefficient values. So we found 0.99, very good straight line, and according to the straight line value and LOD 3s by m, we got the lowest deduction limit 1.7. So lowest deduction limit, what is mean by lowest deduction limits? Why we have to calculate lowest deduction limit? Using my system, I can able to detect up to this level of mercury. Lowest deduction means using my system, I can able to go up to this level. Started from 0.5 micromolar, but it can go up to 1.7 nanomolar. So that's the deduction limit. Okay, the same solution I have taken. This one I added, so it is completely quenched. This K I have taken, and it is, see here, it is around 400. See here, then the system, what I done, it is the fluorescence. Again, it is the S2. So this S2 also it is quenched. This case, two quenching. One is the previous quenching, this one, and another one is the this quenching. So according to this quenching, see here, it is also completely quenched. Then reduction limits, we found this one. The mechanism, see here, aggregation, particle aggregations happen, and this one is the EDX, energy dispersive spectrum. What are the elements are present here? It will show mercury also present here. And this one is the sulfide, after addition sulfide. So this one, I guess it is okay. So two aggregations we obtain. This is another one kind of aggregations. Both are quenching. This one copper and ascorbic acid, sodium hydroxide, sonic acid 1 minute nanoparticles produced. Then this one sulfide having the interaction mercury. This one having the interaction with the ligand. Then it got aggregations. And another one is the copper nanocluster, same one. Sulfide we have taken, and the sulfide also interact with this. See here, this copper. Inside is the copper. If you look well, I written inside 0 and +1, 0 +1, 0 +1. So you may ask one question: why sir you written something? So inside the cluster means it is not like all the atoms. So copper C0 will be there. Then this complex, already we discussed the ligand and copper complex will be there. That copper complex oxidation state is +1. So how much +1 is there, that much fluorescence you can observe. But metal, how much is there, that much fluorescence quenching you can observe. So it is based on your compound. So plus also there, that copper plus sometimes can react with this one, and it is final produce copper sulfide, CuS, it's produced. So this mechanism we propose. Then in references, we have taken 600 folds of cations and 1200 folds of anions, but it never interfere with this mercury and sulfide, one anion, one cations. And we have taken different samples. So one is for the river water samples, and another one is the tape water and bond water. So we obtained good recovery, 98.9 and 99.7. And this is for sulfide. This is also good recovery we have obtained. This is very important point. Please look well, and for me, no objection to explain because it is published work, and I don't have any hesitation to tell some secrets. If you look well, many secrets I am releasing. Many professors not interested to tell that secrets because they can think that many participants may be the competitor for them. But for me, no problem. If you are working with my field, I am ready to help you. It's a competitive word, so I'm also working with you, no problem. So no issue. If it is possible to help you, then I am ready. So that way, I don't have any secrets. I can tell you all the things, how this idea can come for our mind, and what are the things we have done. So smartphone aided paper based kit for on-site monitoring of mercury and sulfide. This is the one secret our paper went for high impact factor. Some reports available with smartphone aided paper. When I was in Taiwan, I prepared this smartphone. It is comes under the category of paper based sensor. People are using microfluidic device, biological people. So the mechanism is go like with microfluidic device. So this is the paper we have cut into the small pieces. It's normal filter paper. Then what my number one. So we have added that nanomaterials inside. I already told you it's green emission, and I have added mercury inside. Then it is a blank and increasing concentration. It is completely quenched here because it is the UV light. That's why the color shown like this one. Then another one also is completely quenched. Okay, it is by UV chamber. But what about paper paste? See here, we have taken small waste PVC pipe. You know, PVC pipe, it's there our home for the water connections as well as electricity connections. We have taken small PVC pipe. The width is the 2 centimeter. Then the this one we have closed, and this end also we have closed. You know that prison is available, that jockey something is there, we just taken. It is waste PVC only. Then we have made one hole in this here by drilling machine to see the color changes, or to keep this mobile phone inside. You know the camera, smartphone is there, so camera is there in the camera. So if you are keeping inside of that hole, you can able to take the photographs. So that technology we have applied. And then you know, well, we need a UV lamp. So we have taken UV LED. We buy small electronic shops. Then that end we just using Solran. The, you know, our mobile phone charger is there. We cut that one wasted one and connected here. This USB we have connected with us our mobile phone chargers. So whichever it is fixing here. See here, my student hand this one, he just hold here. So this USB. When this USB you just blink here, connected here, your LED bulb can blink. It's based on the power we have taken. Okay, the distance we have taken 4 centimeter from here and 1.2 centimeters here. And here it is the hole. This is the small hole. This hole is the 1 centimeter, uh, because this paper thickness it's the 1 centimeter. Then here the holder we just this one we insert inside of the holder. Then exactly it will go, and it will be there in the middle of the bottom corner. When it is blink, then your paper also will be fluorescent. It's based on the color. Thereafter you have to capture that photographs, and in smartphone there is one apps, it's called RGB, red green blue. People they can capture some photographs, then they can find the values of red color, green color, blue color. Then according to that value we have plotted this concentration. So this paper we just insert inside of a smartphone aided kit. This one we prepared from waste material only. The total cost may be 2 rupees I guess. So it's for these LED bulb. Then the smartphone we used, and we also check with the several smartphone, including my Apple and many phones. We just crash check this one, and also we check with the different RGB apps. Then that value we have to plot it, and according to this slope value, and we can calculate the how much concentrations of your mercury is there based on the quenching. That report we have given, and we checked with the several things. So therefore, we prepared a smartphone aided paper based kit. Very simple cost. Even if you are coating your nanoparticles along with coronavirus, for example, this one you see corona carbon nanoparticles, sorry, copper nanoparticles. Instead of this ligand, if I coat the antibody of coronavirus, okay, antibody of coronavirus, or if you want to find the jaundice disease, how much jaundice level is there, or if you want to find the glucose level, then you can quote the enzyme, glucose enzyme, or antibody of jaundice or any disease. Then this one, if you quote here in this paper, then it will be there. After you take the real sample, for example, your blood or serum, if you add inside, if it is really there for glucose, and it will show the different colors, and based on the different color, you can take. But a glucometer these days is available, even though we are not able to give that much small, I mean, less cost amount. Therefore, we can go with other disease, coronavirus or other things. If it is binding together, the color will be changed. Then, according to that way, we can tell this much concentration is there, whether these patients really affected by coronavirus or not. This is like a pregnancy kit. You know, the pregnancy kit mechanism, it's nanoparticles mechanism. Nanoparticles coated with antibody. The lady, if she is pregnant, that time only the enzyme can secrete. That enzyme is called prosteogens. Then that enzyme can bind with this antibody. Then one code will come. If the lady is not a pregnant, the prosteogens will not be there. Only one code there. If two codes is there, means lady got pregnant, and otherwise one's not pregnant. Or in abroad, it will come as a minus or plus. We can decide. The same mechanism we can use using smartphone. Even if I want to measure the sulfur concentration, S2 minus sulfide concentration in a hill, then I can bring my small phone, and this one is just 4 centimeter and 5 centimeter, and with 1 centimeter, I can put it in over my pocket or pant pocket. Then small paper I can bring. There I can tell this much, this much. You can upload this one into your Excel sheet. Automatically, you can find it. Immediately, I can able to tell this one, this much. And also we have validated this method with the microplate reader method. So microplate reader also will show the readings, how much it is there, and we got the good correlation. Therefore, we proved our prepared material, our prepared kit, it's a very good one. It's compared with the other method. And the synthesis part, it is very important. Hope you know, nobody, I mean, some people may report they are foreigners. Within a minute, is it possible to prepare? We done with our small facility only. So everything is possible. Don't think that we don't have facility or something. It is not a matter where you are. It's the thing is how you are. So if you are doing hard work, definitely you can achieve. Okay. At this moment, I can conclude, and tomorrow session definitely it will be with some theoretical background as well as similar calculations of other metal. Tomorrow I'm going to teach you something about the gold nanocluster and gold nanodot, very interesting topic, and what technology we have used, and that one also we have prepared within 10 minutes or something. These days, cluster preparations will take 2 days, 10 days, something else. So we have to keep in the dark room conditions. These things we have written in our paper. That's why it went. Okay. So finally, thanks a lot for giving me an opportunity. My special thanks to Muthusamy, principal sir. Sir already spoke in Tamil. I'm very eager to listen his talk, and he's a nice gentleman. And because of his excellence, supervision, as well as under his head control, they are doing many activities. One for this workshop, and my special thanks to B Ramadevi Madam HOD. She has taken several effort, and finally she approached me, and I guess I done myself best. Thanks a lot, madam. And madam also several time called me, and he has conducted several things, and he arranged many things systematic way. Even I didn't help her for small things. She done the poster preparation. Even I didn't find small mistake from there also. That much experience, madam has it. Thanks a lot, madam. And all the faculty members and the organizing committee of PG department of this college, VSSS Government Arts College. Uh, and my PhD students, Marudupandi, Chandru, Messi, Goglishwaran, and Negi. And MSc students, Kalpana, Mugesh, Manimali, Surudi, Jai Chitra, Rashna, and Sandhya Maladi, Joyce Oscar. And the collaborators from foreign as well as INL, Portugal, and Crescent. These are my publications. And finally, I thank all the participants for your kind attention.
Thank you, sir.
Thank you, madam.
Thank you, sir, for your excellent presentation about fluorescence, chemiluminescence, and the calculation of fluorescence quantum yield from data and relative quantum yield. Then one marvelous work is that is a smartphone edit paper-based kit on side mercury and sulfate, sir. Very interesting session, sir. Thank you very
Thanks,
much.
madam. Thank you, madam.
Thank you. Participants, if there are any question, you can interact
Madam,
with the
I'm
speaker.
checking in the chatting box. If anybody asks the question, I can answer. Otherwise, the dear participants, you can unmute your mic and you can ask. One question I found from Karajiswani. Sir, can we make non-fluorescent material to fluorescent? Yes, you can. If you are tuned the band cap, then fluorescence property will be varied. For example, the non-fluorescent zinc oxide is there and fluorescent zinc oxide is there. So you can tune. What way we can tune it means that is called doping. For example, if you are preparing zinc oxide, already we discussed, many people, they have attended my previous talks also. I have given 6 talks, 7 talks, and many fans also there. Thanks a lot. And they said that wherever you give a talk, sir, we used to come, sir. Thanks a lot, that participants. There I discuss the role of ligands and metal something. If the metal is non-fluorescence, then next time preparation, you have to add nitrogens. The source of nitrogen is ammonia. If you add ammonia, sorry, urea, then automatically it's come for the nitrogen doping. This doping can increase the semiconducting property, then fluorescence property automatically can come. Otherwise, you have to modify the surface ligand. Otherwise, you have to change the protocols. We did not get the first time, even 1 minute synthesis is not succeed with first time. We tried with more than 10 times, 20 times with the different activities. One time we found 10 minutes synthesis. Then my student said that we can keep this one, sir. I said, try with 1 minute. It is possible. Change the concentration A, B. Hope you have seen systematical study will be there. My students always coming with some data. I ask him to go with systematic study. Then now he is familiar. And before I ask him, he is giving the systematic study. What is A, what is B? After mixing, what is A and B? This thing he has given. So therefore, that way you can modify it. Yes, madam. I'm hearing. Hello. Your voice is audible. My voice is audible.
Yes, sir. Participants want to ask questions, please unmute your mic and then ask questions.
Okay. Sivapriya, madam, ask, I am working on organic nanocarriers and I am using dye for the drug to differentiate. I should check the fluorescence properties, sir. Yes, if you are using dye, definitely you have to check the fluorescence property. For example, the drug loading and drug releasing. When I was in Portugal, I learned the cancer therapy. The cancer therapy means several techniques there. One for photothermal therapy, MRI therapy, and another one drug loading and drug releasing. So if you are using this dye as a targeting molecules, then you have to check after loading how much dye efficiency is there. Then after releasing the pH, if you vary it or temperature is varied, the materials can get collapse and drug will release. That time you can check the fluorescence. Is the one way to find out how much drugs loaded, how much drugs releases. So this technology is available. You can use that technology as well as you can check with fluorescence and quantum yield also. You can put it as a supporting information. And Sona Kumar sir asked,
Sir, I am asking question, sir.
Yes, please, sir.
Sir, in silver spectra, how much range is observed, sir?
Silver.
Yes,
You mean silver nano cluster?
yes, sir. My name is Venkatesan, sir.
Yes, sir. Thank you, sir. Generally, we cannot say silver can come this range or that range. Whichever I mentioned, from blue to red, it will be. For my case, this nanocluster, copper nanocluster, some people reported blue, some people reported red. But for us, we got green, but we are not concentrated to change that fluorescence color. So we cannot say, sir, this nanocluster can come this range, that range. It's based on the starting material and also environment as well as the synthesis protocol, sir. All the ranges are available, sir.
Sir,
And,
good evening, sir.
yes, madam.
Very nice session, sir. If you
Thank you,
provide
madam.
your previous links also, we will be very happy, sir. And I have one doubt that
Yes, please.
how can we use magnetic nanoparticles for bioimaging, sir?
Magnetic nanoparticles, the people are using iron oxide. Inside of iron oxide, two types is there, Fe2O3 and Fe3O4. Fe2O3 somewhat little toxic than Fe3O4. So if you have Fe3O4, it is better for biomedical applications. Then second case, that particles is available with cubic structure, spherical structure, rod structure, even sheet structure. So
Yes.
thereafter, you can coat with some dyes on the surface. For example, biocompatible dyes also is available.
Yes.
That type of dyes you can coat on the surface. Then you can apply for the biomedical application, bioimaging application. Then second one, among the different dyes, if you are choosing red color dyes, it is better one, red fluorescent. The reason already I discussed. It can go with a high penetration as well as it's not harmful. That type of things, it's available. Many reports available, madam. Iron oxide they can modify with the dye and they can apply for biomedical applications, bioimaging applications.
Yes, sir. Yes, sir. Which instrument we have to use, sir?
For this one, you have to go confocal microscopy biology groups. They have this fluorescence imaging. Whichever you have seen for fluorescence imaging, all are taken by
Biomedical.
confocal microscopy. I don't have that data, but in my previous talk, I shown that data: cancer therapy, cancer cells, and bioimaging. That one we can do with the confocal microscope. That is available, but all the universities available, even our Kalisalingam, SRM, private universities as well as government universities, they have it, but in cheap cost they are giving. But another one, advanced confocal microscopy also is available. You can couple with the computer, and from computer you can take the image. That things is available, somewhat little expensive, but not like big instrument XPS or TEM. That not like that much expensive. You can take it, madam.
Sir, thank you very much, sir. Sir, I'll send a mail to you. Please provide your previous links also, sir.
Yes, madam. If possible, I have to get the permission from organizing committee because all the authority, madam only, and the previous organizer. If they are allowing me to share it, then I can, madam. No problem.
Okay, sir.
Otherwise, in case of any doubts, I can ready to share my this one PPT something. If it is already published, no issue, no problem. But if this one authority, this institute only, because they only invited me. After discussing with them, and if I no problem, then I can share, madam. Otherwise, you can feel free to write me for any discussion. No problem.
Okay, sir. Okay, sir. Personally, I'll contact you, sir. Thank you,
Yes,
sir.
please. Yes, please. Then anybody? If no question, then I can go for Sono Kumar sir question. You also can see in the chatting box. Sir, when compared to IR, Raman give clear structural information. For sir, nanoparticles, you don't need to go for Raman. Raman, it is only needed for some special case. For example, carbon material, graphene materials needed. IR, it is enough whether your compound is bind on the
More
surface,
questions.
bind on the surface or not. That is enough. Raman, some
One
special
more
cases we needed.
question, sir.
Admin, some disturbance is coming.
Yes,
Just
sir.
ask them to chart it. Otherwise, give a chance to others.
Okay, sir. Participants, if you have any queries, please post in the chat box.
One question from yes, madam, I have seen. Sir, what is the difference between absorption spectrum obtained from UV visible spectroscopy? UV visible spectroscopy and excitation spectrum obtained from the fluorescence spectroscopy. Yeah, it's very good questions. If you observed in my talk already, I given the little details. UV visible spectrum, you can see when it is go from the ground state to excitation, that is absorption. So absorption peak you can get it, and already I discussed. Then excitation means after it reach the excitation state, that time you can get it. So this one excitation, when you are taking excitation spectra, it will ask you to give the emission emission wavelength. For example, if you want to take a excitation spectrum of my nano cluster, first I have to choose the correct excitation spectrum through emission. Then emission I have to fix it. That emission wavelength it will ask. In that particular wavelength, I have to excite it. But UV visible, it started to scan it from 200 to 600 or 800, slow scanning. But this one, if I give 300, directly that 300 nanometer, whichever the electron is there, that particles only can go up and it will get. But UV visible, it is systematic. First UV region and visible regions, it will be scanned. So both are same things, but excitation in a particular emissions, we are exciting. In a emission spectrum, in a particular excitation, we are emitting. So this is the main reasons. When you are taking excitation spectrum, it will ask you to give the emission wavelength. But in UV visible, you don't need to give anything, it will come. So this is a major difference. But the spectrum shapes and the plane almost same, but the peak position somewhat little different. If you are getting 5-6 peaks in the UV visible spectrum, you cannot expect the 5-6 peaks in the excitation. Maybe it's merged together, but same thing. If you want to find it for the fluorescence energy transfer and other mechanism, that time you have to go excitation spectrum. Otherwise, this emission spectrum, it is corresponding to my excitation spectrum. You can revert back and you can get it excitation spectrum. That is enough. My data I given UV visible and emission only. Some people are giving excitation and emission. It is our wish. We can give anything.
Sir, one more question, sir.
Yes, please, sir.
Sir, you saying FR it is a fluorescence resonance energy transfer. You
Yes,
show
sir.
one graph, sir. In donor and acceptor, which is overlap, sir?
Tomorrow class I will discuss very in depth, sir. So three major things needed. One for the donor acceptor, I already told you. Then the merging with UV visible spectrum of donor and the emission spectrum of acceptor should match, sir. So that details tomorrow we can discuss, sir, very in depth. So with clear data, I can discuss you. That is a lengthy study. So then I can explain the details.
Sir, next question, sir. In Stokes, if
Yes, sir.
emission and absorption having same wavelength, having different wavelength, sir.
Emission excitation is different, sir. Excitation, for example, it will be 100 nanometer less than emissions or 50 nanometer less than emissions. And also take examples, if you are giving excitation wavelength 300, then your emission, you should start range from 310 nanometer to the maximum. If you take your Fluoramax, it will go 1200 maximum. If you take JASCO, two instrument is available, one 900 will finish, one will go 1200. So up to the maximum you can give. The 10 nanometer wise, sir, we have to give that difference means this excitation peak also will overlap with the emission spectrum. If you take that emissions, then you will find it. For that purpose, we just go with that one. I can show in my slide one data I shown. If you are look well, then you will know. The first one for our case, yes. This slide see, there is a small hump in this range. So this is the excitation wavelength, sir. If you go below than this one, you can get one more peak, sir. I given 300 nanometer as excitation wavelength, just imagine. So this peak maximum will be had in the 300 nanometer. That is excitation peak. So therefore, when you are giving the excitation wavelength, you just start your emissions after 10 nanometer. Then you will avoid the emission excitation overlap. Okay, sir. I guess this detail is enough for you.
Thank you, sir. Sir, for your student only, sir, I am.
Okay, sir. What's your name, Pa?
Venkatesan, sir.
Okay, great, Pa.
Thank you, sir.
Any other question you can ask, or otherwise I'm finding through.
One of the participants from YouTube, he asked that, sir,
Yes,
have any relation between fluorescence and crystal, NLO crystal?
It is based on the metal, madam. So already I discussed pure metals. It's a good conductor, but nano metal, nano gold, nano silver, it is a semiconductor property. When the semiconductor property is increasing, then little bit complexations properties also can come, because semiconductor properties increasing means it's started to reach the insulator property. For example, the band gap 1 electron volt, it is okay. 2 electron volt is okay. 3 above 3 means it will go for the insulator material. If it is in the semiconductor range, the majority of the report for inorganic nanoparticles, they said that it is a good fluorescent. Metallic nanoparticles, gold metal, silver metal, it doesn't have a fluorescence. But if you are modify their surface with fluorescent molecules, for my gold nanoparticles, no fluorescent, but I coated rhodamine B on the surface. So it is based on your starting material. Starting material itself is fluorescence, though final product also is fluorescent. So that way you can take it. But semiconductor property, if keep on increasing, it goes for the insulator material. That insulator material also no fluorescence. Semiconducting range inorganic nanoparticles, it's fluorescent. Apart from that, the complexations I discussed in this part. For cluster or something report available, it should be a plus and 0. 0 is the copper 0, and this one is the copper complex. Because copper ion, it is not stable here. When you dissolve with water, it will go. But copper complex is stable. So this copper complex, how much plus 1 is there, that much is fluorescence it's there. So inner core is 0, then outer core is the positive, I mean the complex. It's common for gold nanocluster, silver nanocluster, copper nanocluster, something. So this is the mechanism, and these things you can predict by XPS. In my tomorrow class, I can take well details discussion. There, how much percentage this one is there, that much fluorescence is there. In my one work, American Chemical Society publications, there I can explain these details. Any other question, madam?
Sir, one
Sir,
more.
in your smartphone paper-based kit, you have used the mercury and the sulfur.
Yes, madam.
What are the other metals can we use, sir?
Other metals, it is called as a specificity or selectivity. So you know, well, the S group, it's called as a thiol, or we can say as a SH group mercapto. So if you look the SH, yeah, mercaptan. The meaning of mercaptans means that thiol group having high affinity with mercury.
Yeah.
So that's why it is a proved one. So even though other metals is there in this concentration, if you look inside, it is a millimolar level only I have taken. In case if you go with molar level, definitely everything will affect. But for example, sodium, if you take a seawater, it is a milligram, not gram level. It is a gram level. So that solution not applicable to take as a interference directly. For that case, you have to find it how much sodium is there. Then you have to dilute, and diluted solutions you can take it. Similarly, according to the World Health Organization, they have recommended 2 milligrams of mercury, it is okay. 2 micrograms of mercury, it's a tolerance level. But ours is the less, more than 1,000-fold less level also. If it is obtained in the river water or some contaminated water, we can able to find it. For example, one water is there near to our home. It is a lake. we have to wait until it come for the 2 milligrams or something, because these days technology is available milligram level of detection. For example, ICP, inductive coupled plasma, atomic emission spectroscopy. Then when you go with the microgram, then instrument it is not able to detect it. So we have to wait until the river completely polluted. But if you are using this one, if it is reach 100 micrograms, then we have to do the pre-treatments, and we have to remove the mercury. Then you reuse that water. If you are waiting until that one, sometimes we can get some how to say unexpected things. Maybe many living being can die, or some cattle can die. It's many things. So therefore, in the initial stage, so pre-testing it is very important. According to that way, we have given this one, madam.
Okay, sir. Thank you, sir. Can we use this mechanism in the plasma? Now they are using the plasma therapy for COVID patients, sir.
This technology, it's only for the detection, madam. For that technology, you are saying that the testing of coronavirus. Am I correct, madam?
Yeah, yes, sir. They are using
Uh,
plasma technology.
That is different,
Nowadays.
madam. Plasma technology is for the treatment. Our kit is for only testing, not
Testing. Okay,
removal
sir.
of mercury, not removal of sulfur. It is for testing. But that work also we done for degradation application. But plasma therapy, it is the treatment. For that treatment means that is different case. And there is nanoparticles. Well, some people they got funded for coronavirus. They mentioned that they applied copper nanoparticles on the mask. Then some mechanism is available. The coronavirus, after bind in the copper nanoparticles, automatically, because of the immune power and the toxicity, and it will kill the coronavirus. Some things already proved. So this technology is also available. So we can apply this type of small copper things or things, because these days people are using copper plate and many things in daily usage.
Yeah.
So if they are using that technology, it is very good, madam. For treatment is different. That is a big research. We are not interested to go that way. But we done some work with the cancer therapy, cancer treatment, something. This coronavirus, it's a big issue. We have to get the permission, lot of permission, and our institute also have to get a lot of permission to use and bring the coronavirus. That's why not able to do it, madam. It's a
Okay.
health risk only, but people are doing. Really, they are great, and they want to support to the society. So they are not like me. They are really great, and thank for them also, madam.
Okay, thank you, sir.
Any other question?
Chat box, Sachin.
One more question, sir.
We need. Hello, sir.
Yes, sir. Yes, please.
Is fluorescent intensity is affected by nanoparticle size?
Uh, can you explain one more time, sir? Your question not clear.
Is fluorescent intensity is affected by nanoparticle size?
I guess this is not the correct one. You got a little confusion. I just discussed when you are diluting the solution, you got the less fluorescence. The reason is the concentration of nanoparticles concentration is less when you are diluting. But the particle size, even though if you are diluting 10 times, 100 times, 1000 times, particle size are same. The particles numbers only it is different. For high concentration, just imagine I have 1000 numbers of copper nanocluster. But after I diluted only 500 nanoparticles as that. So the particle size will not be varied, only the concentration is varied. When you are decreasing the concentration, fluorescence intensity can decrease. Then otherwise, there is one more technology is called that is new technology, aggregation induced emission, AIE. If you are organic people, that technology is going very fast growing field. Aggregation induced emissions. For example, people are taking phthalocyanine or farbiring and aggregated by some other solvents, THF, other things by simple mixing. But farfarin alone, no fluorescence, and THF alone, no fluorescence. But it produced the nanostructure, because farfarin and THF, it is the Armstrong 10 power minus 10 meter size, but it's combined together and it's coming a big size. That is called by aggregation. this aggregation can produce the emission. This type of aggregations called as a aggregation induced emission. That is the different one. It is for organic work. Then that emission is that particles, nano size particle, you can modify it and you can do the antibody antigens coating. That technology also is going, sir. But the particle size and the emissions, it is not related. The concentration of nanoparticles is related to affect the fluorescence intensity. But the fluorescence intensity decreases is there. For example, my particles is 2.5 nanometer. After getting aggregations, the particle size is 40 nanometer. Then the particle size bigger means it's complex formed copper and sulfide, copper sulfide form. And that case, sulfide and mercury, sulfur and mercury ligand form. Therefore, the inside of Cu0 and Cu plus ratio, it's collapsed. It's getting collapsed. It's converted to all metal or it's getting all converted to Cu plus. Then the system is could collapse, but the particles can agglomerate. That aggregated particles can decrease the fluorescence. These aggregation decrease the fluorescence, but that aggregation, organic aggregation, induce the fluorescence or produce the fluorescence. That is different mechanisms.
Thank you, sir.
Okay,
One
sir.
of the participants, Ms. Madhu, in
Yes.
your presentation slide 53, you are examined by using different metal ions. Among them, Fe3 plus alone trivalent metal. Other are divalent. What about remaining trivalent metal ions?
Yes, it's good question. Actually, we tried with that metal also. If you take lot of things, then it will be a big study. I need to have 10 slides, including all the metals I can include. But we done the major things. We had to look the literature survey. The people already published in high impact factor journal. What are the interference they have taken? See here, the EDTA is not a metal or anion or cation, but I have taken because EDTA having the chelating properties with mercury and sulfur. But even though if you are adding EDTA, there is no effect. This one how I have taken some reports already available. According to that report, I have added. But this Fe2 and Fe3 plus, reviewer asked and myself also thought that why don't we take? Even you can take chromium 3 plus and chromium 6 plus, but chromium toxicity is there means the chromium highly toxic. That one also we done, but not included here. Majority of the cases we done. And the second one, what are the chemicals available at our laboratory, we done. Unnecessary chemicals not to do by, for example, radiative metals here not needed to include. Otherwise, if you take the halogens, other things not need to include. So whichever it is appropriate for this study, mercury sensor and sulfur sensor, that part we had done, sir. Other trivalent metals also we had taken, like chromium 3 plus and other things we tested, sir. But there is no interference we found.
Thank you, sir. Last question.
Yes,
Suman Lada. She
Yes,
asked
yes.
about, sir, can copper nanocluster synthesized with different methods show different sensing properties?
Different method synthesis is not a big problem. After you synthesis, you got to apply for some sensing application. For example, the same one I prepared by room temperature, simple sonication. The other technology is available. People are using 40-degree heating for 24 hours at raw to room temperature. Even though if I take this same ligand and if I use the same method, but majority of the cases their selectivity, I mean sensing provision, it's only go for mercury and sulfur. It's because of the ligand and the inner core of the metals. Even though if you are using different method, one way may produce fluorescent or may not produce fluorescence. In the same method, if you follow for heating method, we don't know whether it's cluster produce or not produce. We done but not produce the same concentration. Maybe the concentration if varied, it may be produced, but we don't go for a long time. So then we chosen this one. That way, once you prepare, the selectivity is based on the outer ligand as well as your inner metal. We cannot say it's based on the synthesis protocol. Synthesis protocol, anything you prepare, finally you have to purify it and apply that one. Synthesis protocol is not a role here. Synthesis protocol is a challenging task to prepare the fluorescent material. Once you prepare, then majority of the cases, same selectivity only will be there.
One more question she asked, sir.
Yes,
Can
sir.
sensing be followed by removal of ions?
That is called capturing, not sensing. That is called capturing. That things also we can do. That is called sensing as well as capturing. Remediation study. Last time I given one talk in Saraswati Narayan College, Madurai. There I just discussed the remediations. Remediation means one problem is there. If I sense this one is the microgram level only is there. In case if I increase, I can able to go somewhat milligram level, but the removal, it is a challenging task. You have to remove the kilogram level, then only you can able to purify the water. If you are having 50 liters of water, if you are only removing 5 ml of water toxicity, then remaining it is a big problem. For that case, you have to go titanium dioxide, water insoluble materials, zinc oxide, something. Then you can prepare huge amount of things, then you can apply. For example, this copper, if I use this one for large scale, then I need to keep, I have to spend a lot of money. If you calculate the normal technology people are using to capture this sulfide and mercury, it will be higher price than that one. Then why the people needed to follow my procedure? So that things also we got to keep it. This technology is not good. Some special cases, for example, pesticides toxicity removal, then people not worry about the cost, and also we have to check the cost also. If you are using gold, I need a 50 kilograms of gold. What can I able to use it? How can I able to use it? Not possible. The same times gold is not suitable. I can able to go for titanium or zinc, whichever it is possible, I can use it. So that type of specific capturing, it is okay. A lot of reports available to remove mercury and sulfur. That's why we are not interested to go that way. And one important synthesis material is 1 minute. The second paper-based kit. Third only is for the mercury sensing and sulfur sensing. These two only is major novel. And our detection limit somewhat far less than the others. These are all the our novelties.
Sir, one more question, sir.
Yes, madam.
Sir, is any specification while selection for metal nanoparticles?
Uh, it's a good question, and it's also secret for me. No problem. I can tell you all the things. We are not worried about the sensing. First, we are concentrating to prepare the materials. For example, our task to prepare fluorescent material with a short time. Then we tried with several. Finally, we found this one is good. After we prepared, we have to try with the several analytes. Whatever we have at our laboratory, we tried. Pesticides, we tried. Explosive, we tried. Toxic anions, cations, we tried. Biomolecules, we tried. Many things we tried. But finally, we got some selectivity with some biomolecules. We got some selectivity with the explosive something. Then we have to look for the literature survey. How much the least level people are reported. If we are not compete with that least level, then our paper will not be able to move it. Then we have to skip that one, and we have to come our side using this technology, whether we have to go for high impact factor. Then my student said that mercury, it is working. Then I told to him only one analyte, it is not suitable to go with the high impact factor. Why don't you try with one anion, one cation? Then I asked him, he tried this one. Fortunately, he found good result with one. Then two analyte with one materials we applied. So that way only we are going with our work. We are not go with the analyte work. So that analyte task, if it is we are going means that is a lengthy study. Then paper will not come large numbers. For example, if we are going with only the jaundice disease, if you are taking, then it is for bilirubin, there is one compound. So many reports available with enzymes. Then if you are going with that direction, it will take long times, then we can able to finish only one work. But if we are going this one, the same times you can able to go with 2 papers, 3 papers, 4 papers. Our AI material synthesis almost 60 to 80%. Then applications remaining percentage. Then major aim remaining that part kit preparations. Now we are doing this kit have to couple with electronic device like your glucometer something. That process is going on. Hopefully after lockdown, maybe we can publish some more paper.
Thank you, sir. This may be the last question.
Yes.
Your student Venkateshan, he asked about
Yes.
in your presentation, one graph show excited photon and
Okay.
emitted photon are same wavelength or not. If take 10 times same readings or different readings.
Yes, he is asking about the fluorescence quantum field calculations. For example, when you are calculating the lowest reduction limit, the formula is 3s by m. S is the standard deviation of your starting material. For example, my nanoparticles I have taken. That nanoparticles I have to take a 15 times reading. So 15 times I have to take a emission. If I am taking 15 times with 1 minute, 2 minutes interval, but I have to get the small difference. For example, this fluorescence, take example, this fluorescent. Yes, this one, the first one I am getting 650. Then the same one, it should come 60, 55, 655 or 649 something. The small difference should be there. But when you are enlarging that one, only you can able to see that is 15 times you have to take. Then standard deviation you have to take. Then from here we got the slope, the concentration. We know well how much we have added. Then absorption fluorescence quenching, it is a straight line. This is slope mx and plus c. So this is intercept and this slope. This m you have to add in that formula 3s by m. Then you can get it. So small changes will be there if you are taking 10 times, 20 times, keep on taking the emission. But the emission maximum, how much times if you are taking, that much times will not be varied. Only with the x-axis, y-axis only will vary. X-axis, it's a constant one.
Thank you, sir.
Okay. Any other question, madam?
Thank you, sir. No question, sir. Thank you, sir. Now I welcome Professor Govindraj to deliver the vote of thanks. Sir.
Hello.
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 I welcome you, sir, to deliver the vote of thanks.
அனைவருக்கும் இனிய மாலை வணக்கம். நமது வாசேசிவ அரசு கலைக்கல்லூரியின் சார்பாக 2 நாள் பயிற்சி பட்டறை நடைபெற உள்ளது. இந்த பயிற்சி பட்டறைக்கு தலைமை தாங்கி அமர்ந்திருக்கும் இந்த கல்லூரியின் முதல்வர் முனைவர் முத்துசாமி அவர்களுக்கு முதற்கண் வணக்கத்தை நன்றியும் தெரிவித்துக் கொள்கிறேன். அடுத்தபடியாக சிறந்த கருத்துக்களை ஆராய்ச்சி மலர் வழங்கிய நம் முனைவர் வாசிமொழி அவர்களுக்கும் நமது கல்லூரியின் சார்பாக நன்றியை தெரிவித்துக் கொள்கிறேன். இந்த நிகழ்ச்சியை சார்பாக நன்றி தெரிவித்துக் கொள்கிறேன். நன்றி, வணக்கம்.
Thank you, sir.
Thank you very much.
Madam, I want to say one thing, madam.
Yes, sir.
So tomorrow talk will cover the fundamentals. Today I discussed. Tomorrow somewhat advanced research. What are the advanced research going on in this field? I am going to discuss. Then fundamental things, Fred, fluorescence, resonance, energy transfer, I will discuss. And charge transfer, I will discuss. And apart from that, gold nanocluster synthesis, I can discuss. And what way? Today I discuss 1 minute synthesis something. So tomorrow also some surprise will be there. So how I varied somewhat different from others, and that particles, how I achieved that things I can discuss, madam. So all participants, it's my humble request, please come by tomorrow also.
Okay, sir. Thank you very much.
Thanks a lot, madam. Thanks a lot for the participants. Thanks a lot for organizing committee and Govindraj sir also.
Okay, sir. Thank you for the participants. Tomorrow we will meet.
Shall we end the sessions?
Okay, bro.